Hello, welcome to another module in this massive open online course. So we are looking at duality, and we have seen the concept of strong duality, that is for any optimization problem written in the standard form, one can come up with an equivalent dual optimization problem which is convex. You can solve that and to obtain the optimal point D star, and if strong duality holds, then now usually D star is less than or equal to P star, where P star is the optimal value of the original primal problem, but when strong duality holds, which is usually true for a convex optimization problem, we have D star equals P star. Okay. And now let us understand that through an example. Alright. So let us look at an example to understand the same, this explore duality. In particular, let us look at the minimum norm problem that we have seen so far. So as an example, let us look at the minimum norm problem, and the problem is the following: minimize norm of a vector A bar. So this is your objective, subject to the constraint A x bar equals B bar. Okay, and you can see these are only equality constraints, there is no inequality constraint. Okay, so this is only an equality, only an equality constraint. To approach this problem, let us form. Now look at this. This has, although this might seem like a single constraint, if A is an m cross n matrix, okay, which means it has m rows, A2 bar transpose, A m bar transpose, correct? Is an m cross n matrix. This is A m bar transpose, and x bar equals B bar. So in reality there are m constraints. Okay, so there are m equality constraints, one for each row of the matrix A, and therefore the Lagrange multipliers for each equality constraint, you need to have one Lagrange multiplier for each equality constraint. So you have a vector nu1, nu2, nu m, where nu m is, or nu I equals Lagrange multiplier for the constraint A I bar transpose x bar equals B I. Okay, so this is for the ith constraint. All right, so you have m constraints, one corresponding to each row of the matrix A. The corresponding Lagrange multiplier is nu I. All right, and therefore you have the vector nu bar, which comprises of the Lagrange multipliers nu1, nu2 up to nu m. Okay. Now the Lagrangian can be formulated as follows. The Lagrangian, that is L of x bar and only nu bar, there is no lambda bar, because there are no inequality constraints. So this is basically the objective function. Now instead of minimizing norm x, one can also minimize norm x bar square, which is basically equal to x bar transpose x bar. Okay, and therefore this you can write the objective function as x bar transpose x bar plus nu bar transpose. Okay, so basically each Lagrange multiplier is multiplying the corresponding row A x bar minus B bar. Okay, so this nu bar transpose is basically your row vector nu1, nu2 up to. So you have each Lagrange multiplier multiplying the corresponding row, and then you are taking the sum. That is what this nu bar transpose is doing. Now we find the minimum. All right, in the first type, find minimum of the Lagrange multiplier of the Lagrangian with respect to x bar. So which means we have to compute the partial derivative with respect to x bar and set it equal to 0. Okay, So, compute the partial derivative with respect to x bar, set it equal to 0. We know how to differentiate this vector this function of a vector x bar transpose x bar. Derivative with respect to x bar is twice x bar plus nu bar transpose A into x bar. So, this is basically your x bar transpose x bar plus nu bar transpose A x bar minus nu bar transpose B bar. Now, of course, derivative of nu bar transpose B bar with respect to x bar is 0. Derivative of nu bar transpose, that is C transpose x bar, with respect to x bar is C bar, which is basically this is your C bar transpose. So, derivative is C bar, which means it is the transpose, that is nu bar transpose A, this is C transpose. So, transpose of this plus or minus derivative of nu bar transpose B bar with respect to x bar is 0. Okay. And this we are setting equal to 0 to find the optimal point. This implies 2x bar plus A transpose nu bar equal to 0, which implies that x bar equals minus half A transpose nu bar. Okay. So, x bar equals minus half A transpose nu bar. Okay. So, that is basically the x bar for which the minimum is achieved for the Lagrangian corresponding to the original optimization problem. Okay. Now, to get the dual optimization problem, we substitute this. So, now what we do is g of nu is basically nothing but you substitute this, that is the minimum value of the Lagrangian. Okay. For that you substitute the x bar. So, that is, so in this, remember, this is your original optimization problem, x bar transpose x bar plus nu bar transpose A x bar minus B bar. In this, what we do is we substitute x bar equals minus half A transpose nu bar. So, that will give you g of nu bar equals, well, minus half A transpose nu bar transpose minus half A transpose nu bar plus nu bar transpose A minus half A transpose nu bar minus B bar. So, wherever there is x bar, I am substituting minus half A transpose nu bar, and this is equal to 1 by 4 nu bar transpose A transpose nu bar minus half nu bar transpose A transpose nu bar minus nu bar transpose B bar, and now if you simplify it, what you will get is basically minus 1 by 4 nu bar transpose A transpose nu bar minus nu bar transpose B bar. So, this is your Lagrange dual function. So, let me just write this again. By minimizing the Lagrangian, what you are obtaining is the Lagrange dual function, which is minus 1 by 4 nu bar transpose A transpose nu bar minus nu bar transpose B bar. Okay. So, this is your Lagrange dual function. Okay. And this will always give a lower bound. Now, remember, this will always give a lower bound. So, g of nu bar is always less than or equal to p star. For any value of nu bar, we will have that g of nu bar, that is the value of this Lagrange dual function. All right. Remember, there are no inequality constraints. So, there is no Lagrange multiplier or there is no Lagrange multiplier vector lambda bar. So, this g of nu bar is a Lagrange dual function, alright. In fact, this is gd of nu bar. So, this gd of nu bar is always less than or equal to p star, where p star equals optimal value of the original or primal problem. Okay. So, this is always going to be a lower bound. Now, what is the best lower bound? And look at this, there is also a concave function, because if you look at this, you can see here this is minus of the form minus nu bar a transpose nu bar. So, this is a PSD matrix, positive semi definite. So, nu bar transpose a transpose nu bar is convex, minus nu bar transpose a transpose nu bar equals is concave. Okay. So, this is concave. So, you can see that this is clearly, and this is of course minus concave function minus nu bar transpose b bar, which is basically a linear function. So, which is also concave. So, basically it is a concave function. So, it is a gd nu bar. So, if you look at this, this is a concave function. Okay. And this is a concave function. This is always a lower bound for p star. Now, one can ask what is the best lower bound? The best lower bound is given by the maximum value once again note that there are no inequality constraints, therefore, we do not have the constraint that lambda bar has to be component wise greater than or equal to 0. Alright. So, I simply have to maximize this Lagrangian dual function, which is gd of nu bar. This is maximized minus 1 by 4 nu bar transpose a transpose nu bar minus nu bar transpose b bar, and now if you to maximize this, if you differentiate this with respect to nu bar, what you get is, well, this is minus 1 by 4 nu bar transpose a transpose nu bar. So, the derivative of that is twice a transpose nu bar minus nu bar transpose b bar, derivative of that with respect to nu bar is simply b bar, and now you equate it to 0, which implies the optimal value of nu bar for which this Lagrange, for which the dual function is maximized, is minus 2 a transpose inverse into b bar. So, we have nu bar is minus 2 a transpose inverse into b bar. Okay. That is the value of nu bar for which the Lagrange dual function is maximized. Now, therefore, the optimal value d star, this is the optimal value of the dual problem, simply substitute nu bar in the dual problem, that is basically this nu bar value of nu bar in the dual problem, that is minus 1 by 4 nu bar transpose a transpose nu bar minus nu bar transpose b bar. So, what you do here is you substitute nu bar equals minus 2 a transpose inverse into b bar. So, if you substitute that, what you have is, it is a little cumbersome, but you can write this. So, nu bar transpose, which is minus 2 a transpose inverse b bar transpose into a transpose into nu bar. So, that is minus 2 a transpose inverse into b bar minus nu bar transpose B bar. So, that is minus 2 A transpose inverse B bar transpose of that is nu bar transpose B bar, and if you simplify this, what you will get is minus B bar transpose A transpose inverse into B bar plus twice B bar transpose. You can simplify this, A transpose inverse into B bar, and that is basically B bar transpose A transpose inverse into B bar, and that is your D star. That is the optimal value of the dual problem. Okay, so this is D star. This is the optimal value of the optimal value of the dual problem. Okay, so this is D star, which is of course always less than or equal to P star. Now let us see what is P star, that is optimal value of the primal problem. We already know that because we have solved the minimum node problem, alright. So this is the optimal value of the dual problem. Now let us go back to the primal problem. Remember, the primal problem is minimize norm x bar square, that is x bar transpose x bar subject to the constraint A x bar equals P bar, and we know that the optimal solution for this is x bar equals this. We know from the previous modules that optimal solution for the minimum node problem is A transpose A transpose inverse into B bar, and now P star, which is the optimal value of the dual problem, that is basically your x bar transpose x bar, and here you substitute x bar equals A transpose A transpose inverse into B bar, and that gives you, what does that give you? That gives you well, that gives you A transpose inverse B bar transpose into A transpose transpose inverse B bar, which you can simplify, and if you simplify it, no wonder what you are going to observe is this is B bar transpose A transpose inverse into B bar. This is P star, and from what you can observe above, this is also exactly equal to D star, B bar transpose A transpose inverse B bar. So this is in fact exactly equal to D star. So we have P star equals D star, and therefore strong duality holds, and in fact one can immediately say that there is a value of the dual problem for, because the dual optimization, because the dual objective function is always less than or equal to the primal. Dual objective always is a lower bound for the primal objective function. So the dual objective and the primal objective are coinciding. That implies that that point is the maximum value of the dual objective function, dual optimization problem, and is also the corresponding point is the optimal value of the primal object. And in this case, P star, we have P star equal to D star, and therefore strong duality in fact holds. And in fact the optimization problem is convex, and that is what we have said. For convex optimization problem, typically strong duality holds. So P star equal to D star, this implies that strong duality holds, and that is what we have already seen, that strong duality holds for this optimization problem. Okay, so this is one of the simplest and the most elegant optimization problems, that is the minimum. Let us look at another interesting problem, and that problem is as follows. let us look at another interesting problem, and that is a linear program. Let us see what duality has to tell us. Now, for a linear program, let us look at the standard linear program, or one of the versions, that is minimize the linear objective C bar transpose x bar subject to A x bar equal to B bar. These are the equality constraints, and then let us say that x bar is component wise greater than or equal to 0. Each component of the vector x bar is greater than or equal to 0. You can write this as a standard form convex optimization problem by saying each component of minus x bar is less than or equal to 0. Okay. Now, the Lagrangian of this can be formulated as x bar lambda. Now, you have both inequality and equality constraints. So, the Lagrangian will be objective function A x bar, I am sorry, C bar transpose x bar plus one Lagrange multiplier for each equality constraint, that is your same as before, nu bar transpose A x bar minus B bar. Nu bar is a vector comprising of the Lagrange multipliers for the equality constraint, plus lambda bar transpose one Lagrange multiplier for each inequality constraint minus x bar, okay, equals C bar transpose x bar plus nu bar transpose A x bar minus B bar plus lambda bar transpose minus x bar. Okay. Each, in fact, the size of the vector lambda bar is equal to x bar, because you have one Lagrange multiplier for each component of xi less than or greater than or equal to 0. Okay. Or we can directly write this as minus lambda bar transpose x bar. Now, we have to take the minimum of the Lagrangian, right, and typically for that we differentiate it with respect to the vector x bar, but since this is a linear, this is an affine function, we will follow a slightly different approach, and that is as follows. And interestingly, if you separate the terms, if you write this as the terms corresponding to x bar plus nu bar transpose A minus lambda bar transpose x bar minus and the constant term, you can see this is affine in x bar, which is basically it's a, you can see this is the equation of basically a hyperplane. This is the equation of a hyperplane, correct. Now, if you see what is, now what we have to do is, now we have to minimize this, okay, and what you will observe is, you will observe something interesting. Now, this is an affine function, it is like a line, correct. So, let us look at this line. If this line has a slope, then the minimum value of this will always be equal to minus infinity, because one of the ends will always be minus infinity. Only if the line is parallel, then the minimum value, that is the line is a constant, okay, and then the minimum value equal to C, that is a constant. Okay. So, this is very interesting, because it is affine. If the vector multiplying x bar is non-zero, then the minimum value is always going to be minus infinity, alright. In that case, it has a slope. If that is 0, that is the vector multiplying x bar is equal to 0, then the minimum value is the constant, which in this case is minus nu bar transpose B bar. Okay. So, with that observation, we have the minimum of the Lagrangian this is, well, if C bar transpose plus nu bar transpose A minus lambda bar transpose is not equal to 0. So, the minimum is minus infinity if C bar transpose plus nu bar transpose A minus lambda bar transpose equal to 0, that is this vector which is multiplying x bar. If this vector is not equal to 0, then the minimum is minus infinity. On the other hand, if If that vector is 0, then the minimum is simply the constant, that is minus nu bar transpose B bar. Now, of course, minus infinity is always a lower bound for any optimization problem, alright. So, this is your Lagrange dual function. Minus infinity is always a lower bound, correct. It is very uninteresting. The interesting lower bound occurs for this, that is minus nu bar transpose B bar, and the best lower bound is available is when you maximize this with respect to nu bar lambda bar. So, the dual optimization problem can be equivalently written as maximize minus nu bar transpose B bar subject to the constraint C bar transpose plus nu bar transpose A minus lambda bar equal to 0, and of course, we always have this constraint as well, that is the Lagrange multipliers corresponding to the inequality constraint are component wise greater than equal to 0, that is each Lagrange multiplier lambda is greater than equal to 0. Now, you can see that C bar transpose plus nu bar transpose A minus lambda bar transpose equal to 0. So, if you now we can simplify this further. So, this implies, what does this imply? This implies that C bar transpose plus nu bar transpose A equal to lambda bar transpose, which is component wise greater than equal to 0. So, this implies that C bar transpose plus nu bar transpose A is component wise greater than equal to 0. Okay. And therefore, now you can simplify this optimization problem as simply this: maximize minus nu bar transpose B bar subject to the constraint that C bar transpose plus nu bar transpose A component wise greater than equal to 0. That is it. And whatever is C bar transpose plus nu bar transpose A, that is equal to, now this quantity is equal to itself equal to, you can set this quantity, once you obtain this quantity, you can set this quantity equal to lambda bar transpose, alright. And in fact, I am just going to take the transpose of this. So, I am just going to take, I can also write this as, because this is a row vector, I can write this as minus nu bar transpose B bar subject to the constraint A transpose nu bar plus C bar, this is component wise greater than equal to 0, and this is the equivalent dual optimization problem. This is the equivalent dual optimization problem. And since this is a convex optimization problem, that is the original problem is a linear program, the dual optimization problem you can also see is a linear program. That is the dual of a linear program is a linear program, it is a convex optimization problem, therefore strong duality holds. P star optimal value of the original original optimization problem you will see is equal to the D star, which is optimal value of the equivalent dual optimization. Alright. So, we will stop here and continue in the subsequent modules. Thank you very much.